All right, good afternoon again, Jonathan and Anna. Yeah, sabi nga ni Jonathan, dami na ng requirements. Yep. And it's toward, especially now that we are, I think, just 3 weeks before the end of the semester. Oh, good afternoon, Noriel. Thanks for joining us. Um, Ayun, parami na parami ang mga requirements, ano, at parami na rin ang parami ang mga chine-checkan namin. Sorry, kakasimula ko pala mag-check ng homework number 6. So I started grading probably around 10 of them. I think it was yesterday or the other day. Kaya lang kakaiba kahapon, nangyari kahapon. Parang simula, anong oras yung una kong meeting kahapon? Pero I think starting at 10 a.m., I'm already online and joining some meetings hanggang mga around 7. Um, pagod na ako. Hindi ko alam. Siguro very uncharacteristic of me. Tulog na ako ng mga 8 or 9 p.m. Nagising ako ng mga 1 or 2 a.m. para lang patayin yung television na nakalimutan kong buksan, na hindi ko na napatay dahil bigla ako nakatulog. Tapos hindi na uli ako nag-work. Hopefully this week I will be able to finish grading homework 6 and homework 7. And then yesterday I already released the problem set number 3. So that's our last problem set for the course. You need to answer 3 numbered items there. Part 1, number 1 is required. That's the quick fire questions. And then kailangan nyo magsagot ng isang question mula dun sa derivative part, tapos isa mula dun sa integral round. So total of 3 problems needs to be submitted. And then I'll create the submission bins within the day, okay? Try to answer it as soon as you can para medyo hindi siya sumabay dun sa mga last minute requirements. But the deadline for that problem set is on June 9th. Binigay ko lang talaga siya ng mas maaga para maisingit niyo siya every now and then dun sa mga requirements niyo. Ano? Yun na lang kasi yung tanging maitutulong ko para medyo mapagaan ng konti yung mga requirements niyo. So that means you need to answer at least one of them every week. So simulan nyo na. Sabit nyo na ng mas maaga para masimulan ko na rin checkan. Ano, I'll promise to prioritize grading problem set 3, lalo na yung mga unang magsasubmit. So that para habang papatapos pa lang yung semestre, nagkakaroon na ng hulma o ng shape yung final grade nyo. We still have a final exam and that will be due on the day the registrar will schedule our final exam. But again, this is just a reflection paper, but be serious about writing it. So I'll give you some guidelines, some guide questions probably later in the week or early next week para guided kayo kung ano yung mga hahanapin ko dun sa isusulat yung problem set, dun sa final project na inyong isusulat. Okay. And then I'm still looking for a couple more homeworks para mapunan ko yung plano kong 8 homeworks. And then I already uploaded homework number 7, which will be due on the 31st. So sa Tuesday, right before midnight, kailangan makita ko yung homework number 7 submitted via Canvas. Hold on, guys. Marami nagno-notify sa akin, pero hindi ko alam kung saan yung gagaling. Galing ba to sa chat box ko? But anyway, I don't know where it's coming from. Okay. Pero yan. Yeah. Okay, so that's the plan. That's the remaining 3 weeks for us for the course, but we still have a good portion of the current module to discuss. So meron pang 2 sections na natitira, though hindi pa tayo tapos dun sa isang section na integrability criteria, no? So meron pa tayong properties of integral and the fundamental theorem of calculus, but I think we can finish it within the week. So pag natapos natin siya within the week, hindi na tayo magkaklase next week unless you want to do some consultations. Pero siguro at most, baka abutin ako ng Tuesday. Kung hindi ko matapos sa Thursday, lahat ng buong Unit 5. Pero yeah, pagka natapos natin ito ng maaga, I will not demand that you still come to class. But you can still email me or message me for consultation so I can open a meeting via Teams. So I think those are the preliminaries. So going back to our discussion, so last time tinapos natin yung integrability criteria, okay? So marami tayong mga nakitang integrability criteria, foremost of which I think is theorem, tama ba? 5.1, yes. That's the integrability criterion. Okay, do you guys still see my screen or nag-ano na siya? Nag-stuck na siya dun sa measure 0? Nag-stuck na yata siya. Hold on, let me restart my screen share. Yeah, thank you, Charles, and welcome to the class. Okay, start on now, reshare. Okay, so tinignan natin yung iba't ibang criteria. Paano natin masasabi ng isang function ay integrable o hindi? Okay, so we found several necessary and or sufficient conditions para masabi na siya ay integrable, but none of them gave us any idea on how to find or to compute the integral, all right? So yun yung parang nalaman nga natin kung siya ay Riemann integrable o hindi, but we don't know how to compute Riemann integrals. So hopefully, we will meet some theorems today na matulungan tayo paano natin mako-compute yung Riemann integral kung alam na natin na yung function ay Riemann integrable in the first place. Okay? So yun yung titingnan natin today. And the first result is Theorem 5.5, which is the Archimedes Riemann Theorem. Okay? So, anong sinasabi ng Archimedes Riemann Theorem? Una, sinasabi niya na si f ay integrable if and only if we can find a sequence of partition inducers such that they will generate a sequence of real numbers, namely the difference between the upper and the lower Riemann sums relative to the partition P sub n will converge to the number 0. Okay? So, sinasabi ng ART o ng Archimedes Riemann Theorem ay integrable lang isang function kung at kung lamang makakahanap tayo ng isang sequence ng mga partition inducers such that the corresponding difference of the upper and the lower Riemann sums relative to such terms in the sequence ay magko-converge kay 0. Okay? Now, this is a little bit, actually, this is something that we can accept. Kasi pwede nyo isipin na, sir, kamukha yan nung sa Theorem 5.1. Ano? Kasi sabi ng Theorem 5.1, ang isang function ay Riemann integrable if and only for any epsilon greater than 0, we can find a partition inducer P such that the upper Riemann sum of f relative to P minus lower Riemann sum relative to P ay less than epsilon. So, ibig sabihin, kaya nating magawang or palapitin yung upper dun sa lower Riemann sum. And we can do this up to any measure of precision we want. Kasi dapat maging totoo daw to sa lahat ng epsilon greater than 0. So technically, the theorem 5.1 guarantees that we can always find a partition na super lapit na nito kay 0. So parang ni-restate lang ni Archimedes Riemann yung theorem na to na okay, ngayon sasabihin ko na explicitly isasali ko na yung konsepto ng limit. So you can think of it as an operationalizing or may ganun bang word? Pag-operationalize noong Theorem 5.1. Kasi ito, maghahanap ka ng partition. Ang kagandahan dito sa Archimedes Riemann Theorem, naghahanap ka nga ng sequence ng partition pero mas mas computational yung pag-check. Kailangan lang natin kunin yung limit ng upper minus lower Riemann sum. Okay? And if we can find a sequence such that this is true, then we can say that f is integrable and vice versa. Okay? And then there's another part to the Archimedes Riemann theorem. It says that if f is integrable, then the Riemann integral, okay, is equal to the limit of the upper Riemann sums relative to the partition, okay, or to the elements of the sequence of partitions we used earlier, and it is also equal to the limit of the lower Riemann sums relative to the sequence of partitions given earlier. Actually, ang tawag natin dito sa sequence of partition inducers na to, such that this equality is true, they are an Archimedean sequence of partition or ASP, okay? Now, kung si f ay integrable, lagi tayong makakahanap ng sequence ng mga partition inducers. Ang tawag natin dito ay Archimedean sequence of partitions. Okay? So, kapag ka nakakahanap ka na ng ASP para sa isang Riemann integrable function f, kunin mo lang yung limit ng mga partition inducers, limit ng mga upper sums relative dun sa mga partition inducers na yun, then you will get the Riemann integral. Or alternatively, you can use the limit of the lower Riemann sums relative to the ASP. Okay? Now, madali lang yung proof ng Theorem 5.5 because here we will just capitalize on our observation earlier that the ART ay parang restatement lamang ng Theorem 5.1 o anong integrability criterion, and it will be more apparent when we look at the actual proof. Okay? Now, the first part is this, which is basically a characterization of Riemann integrability. Dahil characterization siya, kailangan i-prove natin yung dalawang bagay. F is Riemann integrable implies this limit statement is true. And conversely, we need to prove that if this is true, then F is Riemann integrable. And let's start with the direct statement. So in the direct statement, we will assume that F is Riemann integrable on a closed interval AB. Tapos alam nyo na kung ano yung gagamitin ko. Kasi sabi ko nga, ang observation ko rito nung binabasa ko to for the first time, kamukhang-kamukha siya ng Theorem 5.1. So yun yung gagamitin ko. Dahil si F ay assumed to be Riemann integrable, the forward direction of Theorem 5.1 will kick in. So by that theorem, yung integrability criterion, kahit anong epsilon greater than 0, may mahanap tayo na partition inducer such that the upper minus the lower sum will be less than that choice of epsilon. Now for the proof of Theorem 5.5, I will be choosing a specific class of epsilons. So tawagin ko mga 1 over n. So dahil totoo yung Theorem 5.1 sa kahit na anong epsilon greater than 0, then totoo siya sa lahat ng mga 1 over n's. Alright? So dahil totoo siya sa lahat ng mga 1 over n's, we can find a specific partition inducer P sub n for each of the 1 over n's such that this is less than 1 over n. So that's Theorem 5.1 at its finest. Ano? So pumili lang ako ng isang particular epsilon. Ang kagandahan nito, nakakabuo ako ngayon ng isang sequence ng partition inducer. Kasi itong statement na to ay nagiging totoo sa lahat ng n. Lagi akong may makikita na isang partition inducer P sub n. So kukolektahin ko lang yung mga partition inducers P sub n para sa bawat isang 1 over n. Yun yung i-consider ko to be the sequence, right? In other words, P sub 1 will be the partition inducer that will make this difference less than 1, which is n equals 1. Tapos si P2, siya naman yung partition inducer na magiging totoo ito for n equals 2. O yung difference ay magiging less than 1/2, and so on. So nagkaroon na ako ngayon ng sequence ng mga partition inducers such that this is true, which is crucial because Theorem 5.5 asserts the existence of a partition inducer, not a partition inducer, but a sequence of partition inducers. Okay? Tapos ngayon, unti-unti ko itong ginagawa. Nakabuo na ako ng sequence ng mga partition inducers. Okay? And then another thing that we can note is that meron tayong isang lemma before na ang upper Riemann sum ay laging mas malaki sa lower Riemann sum. So, or equal to. So, but the point is the lower Riemann sum can never exceed an upper Riemann sum. So we know that this difference now will be greater than or equal to 0. So meron na akong continued inequality na ito. Okay? And then, I can take the limit of all sides. Okay? So dahil totoo to sa lahat ng n, tapos tingnan nyo itong nasa kaliwa, 0. Limit ng 0 ay 0 because 0 is a constant with respect to n. Yung sequence ng mga 1 over n magko-converge din sa 0. So the left and the rightmost quantities in our continued inequality are both approaching 0 as a sequence. So by the squeeze theorem, the middle guy should also approach 0. Okay? And then we're done with half of the first statement of ART. Okay? Kasi napakita na natin na merong sequence ng partition inducers na limit ay nagiging equal kay 0. Good? Sana ganito lang yung mga pinapa-problem set ko. Ano, ang daling sundan, Now, anyway, so let's go to the converse, yung pakabila. So, ang i-assume naman natin dito ay kunwari, meron tayong sequence ng mga partitions, P sub n, such that this is equal to 0. Gusto natin ngayong ipakita na siya ay Riemann integrable, okay? Pero, again, gagamitin ko na naman yung striking resemblance between Theorem 5.5 and Theorem 5.1. Okay? Na parang restatement lang talaga sila ng isa't isa. Okay, so but in order to do that, I will first interpret this as a statement about the convergence of a sequence. Okay? Ang sequence nga lang natin dito, ito yung formula. Okay? Pero nevertheless, pag in-apply nyo yung definition ng sequence, masasabi natin na given any epsilon greater than 0, there's always a starting index capital N such that the nth term of our sequence starting from capital N, okay, ay nagiging less than epsilon. Okay? So for all n greater than or equal to the starting index that we have found, the term in the sequence will be less than epsilon. Kasi nagko-converge ngayon kay 0, so supposedly may minus 0 tayo dyan na nakaganyan. Definition of sequence. Okay? Now, totoo to sa lahat ng little n greater than or equal to capital N. So this is true for a particular partition inducer, say P sub little n. Okay? So, ibig sabihin, given kahit anong epsilon greater than 0, nakakakita tayo ng partition inducer, in particular, P sub capital N, which we know exists because of the limit definition of a sequence, all right? Or the definition of the limit of a sequence. So therefore, there is such a sequence that satisfies this for any epsilon greater than 0. And basically, ito yung nandun sa Theorem 5.1. Sabi ni Theorem 5.1, pag binigyan ka ng epsilon, lagi ka nakakita ng partition inducer na totoo. Ito, si F ay Riemann integrable. And that's exactly what we have here. So for any epsilon greater than 0, we know that this is true. So therefore, by Theorem 5.1, F is Riemann integrable. Okay? And then finish na. Pass your papers na. Tapos na yung part A. Okay? And again, this is nothing more but a clever use of Theorem 5.1. Okay? Medyo iniwasan lang ng Theorem 5.1 yung paggamit ng limit symbol. Okay? Pero essentially, yun yung sinasabi niya. Now, let's turn our attention to the second statement in the theorem. Okay? Sabi ng theorem, okay, kung meron kang sequence of partition na nahahanap such that this is true, then ang Riemann integral ni F ay equal dun sa limit ng sequence ng mga upper sums o kaya dun sa limit ng mga lower sums, dun mga partitions na dun sa sequence ng partition inducers na kinonsider natin. Okay? Now, ito daw yung proof, ano? Pero medyo may gusto akong mga burahin dito kasi overkill yung ginawa dun sa proof. So start tayo dito. Okay? So part ng assumption, alam na natin that this is true for any epsilon greater than 0 or this guy is true, all right? So that's what we're gonna work out here. Okay. So umpisa natin sa lower sum. Okay? So lower sum, alam ko yung lower sum ay burahin na natin to. Overkill yan. Okay. Didiretso na tayo dito. Okay? So for any epsilon greater than 0, we know that when I add epsilon to the quantity, the new quantity will be strictly larger than the previous one, right? Because here epsilon is something greater than 0, hence the less than there. Okay? Tapos, alam ko na si lower Riemann sum ay supremum na mga lower sums. So therefore, this is smaller than this, or at most equal to this, right? The lower Riemann sum is less than or equal to the lower Riemann integral because this is the supremum, okay? So pag pinalitan ko ito by that guy and then retain the plus epsilon, we'll have a less than or equal to inequality here, okay? Kaya lang ang assumption na natin dito sa part B ay si F ay Riemann integrable. Kasi sinabi dito in that case. So ibig sabihin si F ay Riemann integrable na. So therefore the lower Riemann integral is equal to the the Riemann integral itself. Okay? And then since that is true, then this guy is strictly less than this guy. Okay? So yun yung meron tayo. And then if you transpose this to the other side of the inequality, we'll have lower sum minus integral would be less than epsilon. Okay? And you can put absolute value bars in there. We'll get this quantity. All right? And then you can do the same thing or a similar argument to show that the upper Riemann sum will be within epsilon units away from the Riemann integral. Okay? So that means in the long run, these inequalities will be true. Since this guy will eventually be true for all epsilon greater than 0, ito dapat eventually ay nagiging less than sa epsilon. Kahit anong epsilon pa yung piliin natin. So that means, or you can also apply the definition of the limit. This is true. So therefore, di ba sa sequence a sub n minus a ay less than epsilon? Pag naging totoo yun, ibig sabihin si a yung limit ng sequence. In this case, ito yung nag-i-involve ng sequence n. So ito yung tinitingnan natin as a sequence. So ito yung little a. Ito yung hula natin para sa limit. And this is true for all epsilon greater than 0. So therefore, the limit of L is equal to the Riemann integral. And similarly, in a similar fashion, pero pabaligtad nga lang yung mga inequalities na gagamitin nyo, and instead of a plus epsilon, you're gonna use a negative epsilon, makukuha nyo to. Tapos ito uli yung a sub n minus a, absolute value less than epsilon, si a yung limit. In this particular case, yung Riemann integral, yung limit ng mga sequence ng mga upper sums. Okay? So therefore, totoo yung statement ng Archimedes Riemann Theorem. Okay? So end of proof na tayo. Okay. However, medyo mahirap gamitan pa rin itong theorem na to, no? Kasi ang problema rito sa theorem na to, ang kukunan mo dapat ng limit ay yung upper o kaya lower sums relative to the Archimedean sequence of partition that satisfies this guy. So pag mag-check ka ng integrability, sabi nun ay makakahanap ka ng sequence ng partition inducer such that this is true. Okay? Tapos kung gusto mong gamitin itong statement na to para mahanap yung limit o para mahanap yung Riemann integral, kailangan ang kunan mo ng limit ay yung upper sums relative to the Archimedean sequence of partitions. Dapat yung piece of ends na nakakasatisfy nito, ito yung gagamitin mo dun sa limiting process. Hindi kahit ano basta-bastang partition inducer lamang. Dapat Archimedean sequence of partition. The same thing goes if you want to use the lower sum. Okay? So medyo may kakulangan pa rin, ano? Yung theorem 5.5. But anyway, this gives us an analytic way or a computational way on how to find the Riemann integral. So any questions with that? Clear naman so far? Grabe ang init pa rin, ano? Simula na daw ang wet season pero mukhang balik na naman tayo sa dry season. But anyway. Now, one thing that we can consider would be regular partitioning. You know, so we say that a partition inducer P sub n is regular if and only if there is a common distance between two consecutive partition points. So kung uniform, yung difference ng dalawang magkasunod na x sub n's doon sa partition inducer, then siya isang regular partition. Regular yung tawag kasi merong regular interval between two elements of the partition inducer. So totoo yun kapag meron kang n plus 1 points dito, pero yung common difference between them would be b minus a all over n. Kasi ito daw yung formula para sa bawat x sabay. So basically, we're just subdividing the interval AB into two equally spaced partition intervals. Okay. Okay, so With that in mind, kasi ito yung usual na pinipili natin as elements nung ito usually yung pinipili natin to be the sequence of partitions na kino-consider natin. So kailangan lang nating ma-prove na ang isang regular partition ay pwedeng gamitin as an Archimedean sequence of partition. Okay? So tingnan natin. An example to show this is example 5.10. Ano? So sa example na to, meron ng function x squared. Alam na natin si x squared ay integrable. All right, we have proven it, I think, at least once using one of the integrability criteria before. Para nag-lower at saka Riemann Sum pa nga yata tayo no, para mahanap yung or para masabi na si f ay Riemann integrable, si x squared ay Riemann integrable. So this time, we're going to use Theorem 5.5. So, i-consider ko itong regular partitioning na to. So, using n plus 1 points. So, parang dito lamang ay meron ba si P1, yung unang partition inducer, siya lang ay si, ang laman niya lang ay si 0 at saka si 1. Okay? And this is a regular partition because the distance between the two guys is just 1. It is regular. Ano? Kapag si n ay 2, so we'll start with 0, then we'll have 1/2, and then we'll have 1. Right? So ang distance nito ay 1/2, distance nito ay 1/2, so we have a regular partition. P sub 3 is 0, 1/3, 2/3, and then 1. So meron tayong common interval na, or common difference or uniform step size dun sa mga elements ng partition inducer 1/3, and so on. Okay? So nandito tayo sa x sub I minus 1 hanggang x sub I. Tapos ang itsura niya ay I minus 1 over n hanggang I over n. Tapos gusto nating mapakita na itong sequence ng mga PNs ay isang Archimedean sequence of partitions. Okay? So paano natin yan mapapakita? Kailangan ko lang ipakita na yung limit ng upper minus lower Riemann sum relative to the members of this sequence ay nagiging equal kay 0 or nagko-converge papunta kay 0. So compute natin yung upper minus lower Riemann sum relative to this partition inducer, no? So from we know that this is the formula for the difference. Tapos yung upper sum o yung para sa upper sum ang ginagamit natin ay yung maximum doon sa ith subinterval. In this case, si capital MI, siya yung maximum function value doon sa interval na to. Pero si x squared ay increasing, so the maximum value will occur here. So m sub I will be replaced by I squared over little n. Minus little mi. Pero si little mi, ito naman yung infimum sa bawat subintervals. Pero nga, increasing si x squared, so the minimum will occur at the leftmost point of the subinterval. Kunin natin yung function value ng x na yan, we will have I minus 1 quantity squared all over n. Yun yung little m sub I. Tapos si delta x sub I, ito naman ay yung step size. Okay? Now, ang itsura ng ating mga partition inducers ay I over n. So, ibig sabihin, we will have, say, gano'ng kahaba to? Ito na lang pala, common step size. Gano'ng kahaba yung I over n, yung I minus 1 over n, papunta kay I over n. Note that this is of length 1 over n, so delta x sub I will be 1 over n. And then we simplify this, we multiply it by that guy, take the sum as I going from 1 to n, okay? Since the summation is with respect to I, kailangan niyo yung formula para sa expansion ng sum ng I squared, okay? So, paki-check na lang. When you simplify this summation, you will get 1 over n. And since 1 over n approaches 0, that means the limit ng upper minus lower Riemann sum relative to the sequence of partitions ay equal kay 0. So, ibig sabihin, itong sequence ng partitions na to, actually, which is a regular partition, okay, ay isang Archimedean sequence of partition. Okay? And so, by the Archimedes Riemann Theorem, we can say that x squared is really Riemann integrable. Okay? kahit ilang beses na nating nakita yung Riemann integrability na iyon. But since we have an ASP now, we can continue and now compute for the value of the definite integral or the Riemann integral of x squared over the interval 0, 1. Kasi sabi ng Archimedes Riemann Theorem, yung limit ng upper o kaya limit ng lower sums relative to an Archimedean sequence of partitions ay nagko-converge dun sa Riemann integral, right? So ngayon, titingnan ko, okay, gamitin ko yung upper Riemann sum. Sa upper Riemann sum, kukunin ko lang yung capital M sub I, but we know that capital M sub I is just I squared over N squared times the interval, the length of each of the subintervals. So it's going to be 1 over N. Tapos, okay, constant yung 1 over N cubed with respect to the indexing variable N. So 1 over N squared can come out of the summation, leaving us only with the summation of I squared. Tapos you can check the net, ano yung formula para sa summation ni I squared, I going from 1 to N. Makikita nyo that's N times N plus 1 times 2N plus 1 all over 6. So nawala yung over 6. Tapos all over N cubed, nanggaling yun naman dito. Okay? May division of N cubed sa labas ng summation. And then you take the limit of this sequence with respect to N. So leading coefficient ay 2N cubed divided by the leading coefficient below 6N cubed. So that will give us 1/3. So now we can say that the integral of x squared from 0 to 1 ay equal kay 1/3. All right? Pero syempre, alam nyo na yan, ano? Pero sa Math 155, maangan tayo dun sa mga formulas. Kasi nga, meron tayong meta-axiom of ignorance in effect. So let's pretend, ito yung first time na nakita natin na ang integral ay 1/3. So, whoa, amazing. Equal pala siya kay 1/3. So, yeah, that's a quick example. Now, i-generalize pa natin ng konti kasi napaka-contrived nung paggamit ng upper at saka lower Riemann sum. What if I'm going to use an arbitrary element of the subinterval to give us the height of the rectangles na kinoconsider natin sa pagko-compute ng Riemann integral, ano? So, that's what we will call the Riemann sum, okay? And I will define a Riemann sum of f with respect to a partition P of the closed interval AB as the summation of a function value times the length of the ith subinterval. But this time, hindi ko nakukunin yung maximum function value o yung minimum function value as to what we did for the upper and the lower Riemann sums respectively. Pero kukunin ko yung function value ng isang arbitrary number doon sa ith subinterval. And this tells us na hindi unique yung Riemann integral. Yung Riemann sum. Hindi siya unique kasi nakadepende siya dun sa pipiliin mong C sub I sa bawat interval. Wala tayong restriction sa pagpili ng C sub i's. Hindi katulad ng upper at saka lower Riemann sum na pinipili natin yung pinakamataas at pinakamababa na function value. Dito random na function value yung kinoconsider natin. Okay? Kaya ginamit ko rito ay instead na the Riemann sum. Ano? Kasi hindi nga unique yung Riemann sum. But apparently, it doesn't matter what C sub I we choose because in the limit, when we look at the limit of the Riemann sum, lagi lang itong magiging equal dun sa Riemann integral provided that the function f is Riemann integrable. And that's what is contained in Theorem 5.6, otherwise known as Darboux's Theorem. Okay? Pero isa lang mabilis na remark, alam natin na si f of C sub I ay nasa pagitan ng minimum at saka maximum over the interval. Okay? So, or the infimum and the supremum within the interval. So, kapag minultiply ko both sides ng delta x sub I, walang mababago na inequality, then I take the summation of all sides, then makikita ko na yung lower Riemann sum is less than or equal to the Riemann sum, or to our Riemann sum, which is less than or equal to the upper Riemann sum. Okay, so natural naman tong statement na ito. Now, gagamitin ko yung remark na to in one part of the proofs of Darboux's theorem. Pero ano ba yung sinasabi ni Darboux? Ay sinasabi ng theorem niya, etong tatlong statements na to ay equivalent with the premise that f is bounded. Okay? So kapag ka daw si f ay bounded, f is integrable if and only if this statement B is true, if and only if this statement C is true. Okay? Ano ba yung sinasabi ng statement B? Sinasabi niya na ang limit ng upper Riemann sum minus the lower Riemann sum is equal to 0 provided that P sub m is the nth regular partition of closed interval AB. Okay? But this is already covered. Covered na siya ng Theorem 5.5 ng Archimedes Riemann Theorem. Kaya sabi ni Archimedes Riemann Theorem, f is Riemann integrable if and only if there exists a sequence of partitions P sub n such that the limit of the upper minus the lower Riemann sum is equal to 0. Essentially, statement B is just a particularization or an instant case ng Theorem 5.5. Kasi sabi ng Theorem 5.5, basta may mag-exist na sequence of partitions na sinasabi ng statement B, nth regular partition. So mas specific atong statement B. So basically, you can think of the truthfulness of A if and only if B to be inherited or to be a corollary of Theorem 5.5. Okay? So kaya tapos na tayo dun sa unang part ng equivalency. So we have proven that A and B are equivalent, or the proof can be easily written down by just citing Theorem 5.5. So that's done. But however, Darboux's theorem tells us the equivalency of the three statements you see in here. So kailangan kong makonect si C or ma-prove na si C ay equivalent either kay A o kaya kay B. Kasi pag na-prove ko na si A ay equivalent kay B, na si C ay equivalent kay A, pero alam ko si A ay equivalent kay B, so by hypothetical syllogism, si C ay equivalent na rin kay B. Or if I will be able to prove that C is equivalent to B, then hypothetical syllogism, two ways, can tell us that B is equivalent, that A is equivalent to C. So pili na lang tayo ng anong ipoprove. Equivalency ni A at saka C o equivalency ni B at saka ni C. Now, ang pinili nung lecture notes ay ipakita na si B ay equivalent kay C. And that's what we will try to follow. Okay? So, let's start by proving B implying C. Tapos homework nyo yung C implying B. So that will be homework number 7. And I will tell you what my problem with the proof given in the lecture notes nung C implying B. Kung bakit ayoko siyang tanggapin. At least for now, hindi ko pa maisip kung bakit siya totoo. Actually, nakalimutan ko siyang pag-isipan. Na nung binabasa ko to before the class on Thursday, na-note ko na may something. Tapos, nakalimutan kong pag-isipan siya uli. Kanina ko lang naalala na may duda nga pala ako sa proof na to nung nagklaklase na ako dun sa kabilang section. Kaya sabi ko dun sa kabilang section, homework nyo na lang yung C implying B kasi hindi ko pa naisip yung reason kung bakit totoo yung proof na nandito. But I'll tell you later what my reservations are or my reservation is. Okay. Pero madali yung B implying C. Sa B implying C, ang assumption natin ay dun sa nth regular partition o yung limit ng upper minus lower Riemann sum relative to the nth regular partition ay magko-converge kay 0. Okay? Gusto kong ipakita na ito ay nag-exist at independent siya ng choice ng C sub I. At also equal din siya dun sa Riemann integral o yung limit ng Riemann sum ay equal dun sa Riemann integral. Okay. Now, nasabi na natin kanina na ito ay totoo. Alright? Yung lower Riemann sum ay less than or equal to Riemann sum, less than or equal to the upper Riemann sum. And this is true whatever the choice of C sub I was to come up with the Riemann sum. Okay? So kahit ano pa yung C sub I. So this inequality is really independent of the choice of the C sub i's that will come into play in computing the Riemann sum. So therefore, this guy is true regardless kung ano naman si C sub I. Okay? Tapos, kukunin lang natin yung limit ng tatlong sides. Okay? which I know, okay. So, kunin natin yung limit muna nung nasa kaliwa. Limit na to ay equal kay Riemann integral. Bakit? Kasi alam ko na ito ay totoo. Yung statement B raw ay totoo. Pero si statement D will imply statement A. Kasi assumption na prove na natin yung equivalence ni A at saka ni B. So since this is true, we can say that F is Riemann integrable. And since F is Riemann integrable, then the limit of the lower sum is equal to the Riemann integral. Limit ng upper sum ay equal sa Riemann integral. Itong dalawang ito, nag-exist yung limit at saka equal. So by the squeeze theorem, the limit of the one in the middle, yung palaman ng sandwich, so ito ay nagko-converge din. And by squeeze theorem, nagko-converge siya dun sa common limit ng mga pang-sandwich sa kanya. So therefore, this R, or the Riemann sum, will converge to the limit of the lower and the upper Riemann sum, which both happens to be the Riemann integral. And so we have established yung B implying C. Okay? Ganon kabilis. Ngayon ang problema, yung pakabila, C implying B naman. So gusto ko ipakita na kapag ka yung limit ng Riemann sum ay nag-exist, okay, at yun ay equal dun sa Riemann integral, then dapat yung limit ng upper minus lower Riemann sum ay equal kay 0. Okay. Now, meron siyang pinigay dito na proof. Ito lang yung hindi ko matanggap dun sa proof, yung hindi ako sigurado. Sabi niya ay, for every n, choose C sub I so that f of C sub I ay equal kay m sub I minus 1 over n times B minus A. So kasi totoo to sa lahat ng Riemann sum, regardless of the choice of the C sub i's. Now, what the proof is trying to do is to instantiate it to a specific C sub I. Kasi kailangan niya makahanap ng partition na ito ay totoo. Okay? So kailangan niyang tingnan ano yung itsura ng upper sum at saka ng lower sum. So kailangan niyang i-connect yung Riemann sum doon sa upper sum at saka lower sum. And the way the proof is trying to do this is to instantiate a value of C. It is telling us to choose C sub I to be that X value within the ith subinterval whose function value under F is equal to this guy. My question here is, sure ba tayo na may nag-exist na C sub I na totoo ito? Yun yung tanong ko, yun nag-exist ba na C sub I na totoo yan? Kasi kung kaya niyong sabihin sa akin or ipaliwanag sa akin kung bakit totoo ito, kung bakit may nag-exist na C sub I na ito ang function value, then the rest of the proof will follow nicely. Okay? Kaya lang hindi klaro sa akin eh. Hindi ako makapag-IVT. Kasi kung makakapag-IVT lang ako sana, baka kaya kong ipakita yon na may nag-exist na C na ito yung totoong value. Kailangan ko lang ipakita na this guy is between little m at saka capital MI. Okay? If that is true, yes, then I can conclude that there exists a C sub I. Pero para magamit si IVT, kailangan si F ay continuous. Alright? Alam ko ba na si F ay continuous? Hindi. Ang alam ko lang ay si F ay bounded. Meron ba tayong theorem? Tandaan nyo ba guys, meron ba tayong theorem na nagsasabi na kapag ikaw ay Riemann integrable, then dapat ikaw ay continuous? Actually, wala, no? Kasi meron nga mga Riemann integrable function na hindi continuous. So, hindi tayo sure talaga kung si F ay continuous o hindi. So, hindi ko kayang gamitin si intermediate value theorem. Okay? So, do you see my point? Kung bakit hindi ko pa matanggap for now yung proof ng C implying B dun sa handout, ano? I might just be missing something. So kung naisip nyo kung bakit may nag-exist, di tapos na kayo sa homework, kakopyahin nyo na lang yung rest ng nandito. Tapos, ikwento nyo sa akin bakit totoo yun. Otherwise, I'm thinking of an alternative proof. Pwede kong hatiin to sa dalawang cases. Hold on. Okay. Pwede ko kasing tingnan si capital M sub I kasi. Kahit sinasabi ko siya ay maximum paulit-ulit, hindi nga pala siya necessarily yung maximum. Siya yung supremum. Siya yung least upper bound. Okay? So, pwede natin gamitin yung characterization ng least upper bound na kapag siya ay least upper bound na, pag nag-minus tayo ng something na maliit sa kanya, hindi na siya magiging upper bound. So, ibig sabihin, there must be some function some number c sub I in the domain such that si f of c sub I ay equal dito to something smaller than m sub I. Pero I might need continuity there. So, yeah. Yun yung iniisip ko na, okay, may mahanap ako, pero hindi talaga clear sa akin kung bakit ako sure na may f of c sub I. Probably we can say that f of c sub I will be less than or equal to m sub I minus 1 over n times b minus a. Provided itong difference na to ay hindi lalampas ng m sub I. So, pwede ko itong dagsungan na, okay. Pwede kong sabihin na, okay, let's choose c sub I such that c sub I has function value between these two guys. But again, you need to tell me why we are sure that there exists a c sub I na yung function value ay nasa pagitan nitong dalawa. Ito ay clear. Ito ay somewhat clear. Pwede nyo sabihin na, yeah, ano lang yan, characterization ng infimum. Okay? And then I think that will be better. Kailangan nyo lang dagdagan ng konting detalye. Ano? So yan yung homework number 7. You need to write a proof, a rigorous proof of C implying B. Sana tama yung nasulat ko. So, yun yung nasulat ko doon sa... Yun yung nasulat ko doon sa Canvas. So, yan yung homework number 7 nyo, which will be due on Tuesday next week. Alright? So, kindly think about it para alam po na yung isusulat ko sa susunod na iteration ng handout. Pero mukhang hindi yata ako magtuturo ng 155 next semester. So, para na dun sa susunod. Ano? Para pag pinamana ko itong namana kong lecture notes, medyo nakorek ko na yung mga nakita natin na typos. Okay? Alright, so I hope the homework is clear. Hold on guys, pag-record ba tayo? Yes. Okay. Okay, and then once you have proven that, now we can have the following identity. Ano? So kapag si f ay integrable, meron na tayong tatlong alternative ways on how to compute the Riemann integral. It could be the limit of the upper Riemann sum, the lower Riemann sum, or the Riemann sum relative to a regular partitioning. Okay, so kunin nyo lang yung mga limits na yan. And one application of Riemann integrals is to calculate or evaluate the sequence of some complicated sequences, specifically sequences of partial sums. Ano? So for instance, sa equation 5.11, halimbawa, mandadaya ako ng konti, buburahin ko to. Halimbawa, gusto mong kunin yung limit ng sequence AN, where AN is a sum for any n. Okay? So parang meron kang A1, si A1 ay equal kay 1/2, si A2 ay equal kay 1/3, plus hanggang umabot ng 1/4. So hanggang 1/4 ito. Okay. So I'm just plugging in n in here, okay, dun sa summation. Tapos si A3, magsisimula siya kay 1/3 plus 1, so that's going to be 1/4, all the way up to 1/2n, so that's all the way to 1/6. So this 1/4 plus 1/5 plus 1/6. A4 is 1/5 plus 1/6 plus 1/7 plus 1/8, and so on. Yan yung itsura ng mga ANs, or at least a few ANs. Now, if the problem is to find the limit of the a sub n's, tapos maang-maangan nga tayo dito, hindi pa tayo kunwari marunong ng sequences, ano, ng pagkukuha ng sum na ng sum ng series. Alam na natin yung sequences, series yung hindi pa natin alam, ano. So kasi siya ay sequence lang siya ng mga parang hindi ko na nga sasabihin kasi mandaraya tayo if ever, ano. So para makuha yung limit ng mga ANs, pwede tayong gumamit ng Riemann sums, okay? Kailangan ko lang gawin ay ipakita na bawat isang term ni a sub n ay pwede nating masulat as a Riemann sum. Okay? Tapos, pag napakita na natin na bawat an ay isang Riemann sum, so yung limit ng Riemann sum ay equal sa limit ni an. Pero ang limit ng Riemann sum ay equal sa Riemann integral. Okay? So yun yung goal natin dito. So, what we'll do now is first, try to write this guy in summation notation para ma-compare natin siya doon sa form ng Riemann sum. Okay? So, ito yun. Yung sum na yan, pwede kong isulat in sigma notation as this guy, right? So, the summation will start at 1 over n plus 1, the starting value of I, and it will end at 1 over n plus n, which is 1 over 2n, the terminal term in the formula for an. So basically, ito yung sigma notation para kay an. Tapos, kailangan ko itong isulat as if it is a Riemann sum. So Riemann sum, dapat na kinonsider ng Darboux Theorem, regular dapat yung partition. So kailangan meron akong delta x sub I, right? Tapos siya dapat ay equal sa I sa 1 over n. Kasi ito yung length ng isang regular partition. Alright? So that's why I forced the issue here to factor out 1 over n. Okay, so nag-factor out lang ako ng n mula dun sa denominator, ito yung natira. And I did so that I already have the desired term for delta x sub I, or the desired expression for delta x sub I. Tapos ngayon, ito yung magiging f of ci na gagamitin natin para magmukha siyang Riemann sum. Okay? And in this particular case, dahil ang nagbabago lang naman dito ay ito yung pipiliin kong c sub I. Si c sub I ay I over n, which we know is between 0 and 1. Swak na swak doon sa ating regular partitioning. Okay? So pag ang pinili mo delta x sub I ay si 1 over n, okay? Ang pipiliin mo dapat c sub I ay si I over n. So whatever the remaining factor is, yan yung gagawin nating function f ng input ay si I over n. So therefore, our function f of x will be 1 over 1 plus x. Ito yung ito yun. So now we see that each of the a sub n's is a Riemann sum, right? With common increment 1 over n and the function 1 over 1 plus x na ginagamitan na nagdedetermine kung ano yung second factor inside the summation. So when we take the limit of a sub n, we are essentially taking the limit of the Riemann sum, right? And this is the Riemann sum of 1 over x plus 1. And limit ng Riemann sum relative to the function f, which is 1 over x plus 1, ay integral ng 1 over x plus 1 from 0 to 1. Binura ko yung nandito kasi kunwari hindi nga tayo marunong mag-evaluate ng integral. Okay? But you know that this is equal to ln 2, ano? Dahil equal siya kay ln 2, alam natin na yung a sub n's, however complicated they look like, will only converge to ln 2. Or, if you want to be strict in complying to the meta-axiom of ignorance, yung a sub n ay nagko-converge doon sa Riemann integral ni 1 over x plus 1 from 0 to 1. All right? So, yung trick natin dito, sinusulat lang natin yung bawat term as a Riemann integral prior to taking the limit. Kasi alam na natin yung limit ng Riemann sum. Kailangan ko lang makita ano yung function f na kailangan nating i-consider. Okay? Now, another example is this one. Okay. Ito, napaka-komplikado na nung expression na yan. Pero partial sum pa rin naman siya. Ano? So, nag-start, ano bang pinagkaiba? Dito lang sila nagkaiba-iba sa exponent doon sa loob no exponent para kay e. Nag-start sa 2, tapos nagiging even siya 2, n plus 2, n plus 4, n plus 2n. So, kailangan natin itong isulat in sigma notation. Ano? So, note that could be written this way. Okay. Unang term ay 2 over n times nth root ng e to the power n plus 2 times I. Kasi dapat when I equals 1, so dapat ito ay n plus 2. Okay, there we go. That matches, okay? We keep on summing up. When I is equal to 2, this will be n plus 4. We get the second term. And the terminal term will happen when I is equal to n. So we'll have n plus 2n, which is exactly the terminal equation, the terminal exponent here. So everything fans out. It seems that tama yung sigma notation natin dito. And then I'll try to manipulate it a little bit para mas clear sa atin anong klaseng Riemann sum siya, ano. So note that loss of exponents, this is a product, nasa loob siya ng radical. So pwede ko silang paghiwalayin into separate radicals. So, but this guy simplifies to e, okay? May constant na 2 sa taas. So itong constant na to pwedeng lumabas ng summation. We'll get that guy, all right? So what we'll be left with is 1 over n times this guy, which is fine because we know that 1 over n is the desired length of the ith interval kung regular partitioning siya. Kasi ito yung length ng bawat interval para sa isang regular partitioning ng interval 0 to 1. Okay? Para hindi na kayo mag-consider ng ibang interval, i-factor out nyo na lahat ng sobrang factors. Halimbawa, yung 2 over e, you could have chosen that to be your regular interval or your regular step size. Kaya lang kailangan yung i-adjust anong klaseng interval yung na-partition. Pero sure na tayo ng regular partitioning ni 0, 1 ay laging may length na 1 over n. So para hindi ka na mag-isip ano dapat yung tamang partition kasi kailangan mo pa siyang i-translate at i-scale. Okay? So to avoid that, okay, 1 over n na lang yung gamitin nating delta x, okay? So lahat ng constants ilabas natin. Yun yung nangyari dito. Lumabas yung 2 over a. Tapos, ito yung function f dapat. Ayan yung c sub I, ano? Tapos sabi natin na pag-usapan na natin na yung c sub I ay equal kay 1 over n. O sorry, kay I over n. So ibig sabihin, ito yung magiging variable. So ibig sabihin, ang f of x natin ay e to the negative 2x. So Riemann sum na siya. Ito yung delta x, ito yung f of c sub I. Sorry. Sorry about that. Umatake yung, hindi ko na alam kung ano umatake. Pero anyway. So yan yung function na i-consider natin. So pag kinuha natin yung limit ng a sub n, we're effectively taking the limit of 2n times a Riemann sum. And we know that this guy, or the limit of the Riemann sum, is just actually the integral. Okay? In particular, that's going to be the integral of 1 over e to the 2x from 0 to 1. Pwedeng wag nyo nang isama yung dx kasi 155 na naman tayo. Ano? So yeah, there we go. That's one application ng Riemann integral. Paghanap ng sequence. But of course, you know, from elementary calculus, mas maraming real-world applications pa ang integrals. But for now, maybe that's our theoretical, or that's the theoretical significance that we can attach to Riemann integrals. Okay? Any questions? Okay, if there are no questions, then I think I'll stop here. Okay, so medyo matake na kasi saka ganito rin yung ginawa ko kanina. Ano? So ni-stop ko na muna because I think we only have a a couple sections to go, but they cover 7 pages lang. Properties of Riemann integral. Okay. Tapos, ipapa-reading assignment ko na lang yung Theorem 5.8. Yung detalyadong proof naman ay nandito. I checked kanina itong proof. Mukhang tama naman yung proof, so that's fine. And then you'll have the mean value integral, and then we can end up with the fundamental theorem of calculus. So I think 2 days will be more than enough to finish the remainder of the course. So that's why we can chill a little bit today. So tatry kong tapusin yung course Thursday para hindi na natin kailangan mag-meet ng mga susunod na linggo. Sayang naman. Pero I'll be available if you have questions or for consultations. I can open up the meeting. And anyway, may utang pa akong isang homework sa inyo, homework number 8. So I can announce that via Canvas. But yeah, at the latest siguro we will end the semester on Tuesday next week. Pero I'll try to do it on Thursday, okay? But again, feel free to contact me about anything until June 9th, or even beyond. So yeah, kahit hindi tayo nagbi-meet live sa mga classes, okay? So if there are no questions, then I'll meet you guys on Thursday again. And then until then, keep safe and take care always, okay? Yeah, thank you, Jonathan and Charles. Parang kayo na lang dalawa yung natira or meron akong hindi nakikita sa chat, okay? But anyway, bye guys, and continue recording.